Okay, section 10.4, reactions with gaseous reactants and products, okay? So we're gonna use the ideal gas law, the ideal gas equation, in order to make measurements in chemical reactions. So the example that your textbook lays out for you is a nice one. It's a relatively simple equation. It says that 2 moles of carbon monoxide gas will combine with 1 mole of oxygen gas to form 2 moles of carbon dioxide gas. So all reactants and products in this reaction, in this equation, are gases. Okay, so here's what's happening. 2 of the carbon monoxides are combining with 1 of the oxygens to form 2 carbon dioxides. Now, I'm going to show you one way to think about this. So there's a carbon, there's an oxygen. Here's a carbon, here's an oxygen. So 2 molecules of carbon monoxide, right, are going to combine with 1 molecule of oxygen. So there's 1 molecule of oxygen. What happens? One of the oxygens can combine with the carbon, the other oxygen can come over to that carbon, and so now what we have are 2 carbon dioxides, right? Conservation of mass, right? Remember that relationship? Meaning you can't have more atoms on one side than the other of the same element. So 2 carbons on both sides and 4 oxygens on both sides. Now that's number of molecules, but what I'm going to claim is that we can also use this equation for the number of moles. Because essentially what we would be saying is, if we have 2 moles of CO, a mole, what is a mole? 6.02 approximately, I'm rounding it. 6.02 times 10 to the 23rd molecules. So if you have 2 moles of CO, all we're saying is that you have 2 times 6.02 times 10 to the 23rd molecules. And since the relationship is that you need 2 molecules of this one for every 1 molecule of that one, that means that 2 moles of CO is going to react with 1 mole of O2. 1 times 6.02 times 10 to the 23rd molecules. So even though the balanced equation is telling us the number of molecules that react and are formed, the relationship between how many do, we can scale it up to moles as well. It's 2 moles of CO for every 1 mole of O2 for every 2 moles of CO2. So let me write it this way. 1 mole O2 for every 2 moles of CO. That's one relationship we have here. However, if you remember Avogadro's law, Avogadro's relation, the volume of a gas is directly proportional to the number of moles. So if I double the number of moles, I double the volume. Or if I cut the number of moles in half, I cut the volume in half. So what we can also do is we can say that this is the same as the volume of O2 that reacts with the volume of CO. So we can write it this way. 1 liter of O2 will react with 2 liters of CO. That's Avogadro's law, okay? 1 mole of O2 reacts with 2 moles of CO. That's from the stoichiometry of the reaction. But via Avogadro's law, we can also say that 1 liter of O2 will react with 2 liters of CO. Now, this is interesting because what that means is, if you were to have a balloon with O2, Okay, so it has that volume. That's the size of the balloon. And you wanted it to react completely with CO. Every molecule of O2 reacts. At the same temperature and pressure, the amount of CO that you would need would be twice as much. Okay? Twice as much, right? Because it's a 1-to-2 relationship. But what would happen in terms of CO2 when they react? When they react, here's what we can do. Look, there's a 2 there, a 1 there, and a 2 there. So we could also say that the amount of CO2 that you produce, the volume, would be the same as the CO. I made that a little bit bigger. Let me make this balloon a little smaller just so that you can see. There we go. These two volumes here are supposed to be the same in my little pictures here, okay? Again, because there's a 2 here and a 1 here, or a 2 here and a 2 here. These two are equal to each other. So the volumes are equal. Now, that's also true in milliliters. So I could say 1 milliliter of O2 is going to react with 2 milliliters of CO. This only works for gases. The volumes are proportional to the number of moles in the balanced equation for gases. You can use that relationship. Okay? So let's take a look at a quick little example here. Suppose we were told, make some space in here. Suppose we were told that 65.8 milliliters of CO reacts. How many milliliters of O2 reacts according to this equation? Okay. Well, here's what we would do. We would say, hey, we've got 65.8 milliliters of CO, and the relationship between O2 and CO, since we're in milliliters, is it's 1 milliliter of O2, 1, reacts with every 2 milliliters of CO. And so you would get 32.9 milliliters of O2 reacts. Very simple relationship. And again, you can't do that with solids and liquids. You can only do it with gases. So the stoichiometry of the equation, very simple relationship for volumes as well. Now, this also can be extended to reactions that do not involve completely gases, but we also have to reintroduce some of the concepts we learned back in Chapter 3. So, for example, suppose we're looking at this equation here. Sodium, which is a solid, reacting with chlorine, which is a gas, to form sodium chloride. Now, I've balanced the equation already. Okay, so that's already done. And suppose we're told that we're given the number of grams of sodium. Suppose that's given. Can we relate that to the amount of chlorine gas that's going to react with it? Well, we can via, again, Avogadro's law. So what you can do is you can say, wait a minute, we're given the grams of sodium. So I'll write it again down here. We could convert that to moles. So if I multiply that by 1 mole of sodium over its molar mass, what does that give me? I'm going to write that in parentheses. That conversion factor right there gives us the moles of sodium, right? Then what we could do is we could say, wait a minute, there's a mole relationship here. Not a volume relationship because one of these is a solid, so we can't use that relation, but we can use a mole relationship. It's 1 mole of chlorine gas for every 2 moles of sodium. Now, we did this back in Chapter 3, right? And we even did it a little bit in Chapter 4, but mainly Chapter 3. So that will tell you how many moles of chlorine gas you have. Now what you could do is you could reintroduce the ideal gas law. For a gas, the volume of a gas is equal to the moles of the gas, N, times the gas constant R, times the temperature T divided by the pressure P. So in other words, I could multiply this by RT over P, and that would give me the volume of the chlorine gas. Okay, so sometimes you will see as you go through these practice and sample problems and ALEKS problems, you'll see that they may ask you, given the mass of one of the reactants, can you find the volume of the gas that's also going to react with it? And so this is how you would do that. Okay, now the last issue here that I'm going to raise is sometimes what happens is the pressure of a gas will change during a reaction. Okay, so what we can do is we can say that if the pressure of a gas changes during the reaction, we can use the ideal gas law, PV equals nRT, to make predictions. Okay, so for example, suppose I said this, N is equal to PV over RT. And suppose I say that the pressure changes. It could go up, it could go down. If the gas is getting produced, it'll go up. If it goes down, if the amount of gas goes down, the pressure will go down. So I'm going to write that as delta P for change in pressure. So what I can do is I can extend that to this. Delta N, that's the change in the number of moles of a gas. How much is consumed or produced in the reaction. So let's say you start off with 1 mole and you go up to 2 moles because it's being produced. Or let's say you start with 2 moles and it goes down to 1 mole because it's being used up. It's being used in the reaction. It's a reactant. This would be equal to the change in the pressure, delta P, times, so I'm going to put this in parentheses, times V over RT. Okay, so in other words, if you see a problem where they say, hey, the pressure went down by 0.2 atmospheres, how many moles of the gas were used up? You could use this equation. You could put your change of what the pressure change was, multiply that by the volume of the container, divide that by RT, and that would give you how many moles of the gas were used up in the reaction. Okay. So there you go. So these are reactions with gaseous reactants and products. Really, we would call this gas stoichiometry. So if you're researching this on your own, we would call this gas stoichiometry. It's really another example of the ideal gas law.